Hello, my name is Mushahid Rasul. This is Homework 7, Part 1. Here we are required to make a 4-bit shift register that can clear its contents, load the value from its input, and shift to the left. Here I have my code for the shift register. All I'm doing is declaring ports. Ports are clear, load, shift left, clock, and a 4-bit input that's going to give a 4-bit output. And here I have a temp signal, and then I have if clear is equal to 1, then temp should be 0. And then on the rising edge, if load is 1, it's going to take the temp signal, whatever was inputted, the 4-bit input is going to be saved into temp. And then if shift left is enabled, it's going to shift all the values, all the bits to the left. And that's basically what the shift is doing. And here's my test bench. I've implemented a component, assigned the variables, and alternated the clock here. And then I just gave it a example of a 0001. And then when I simulate this, it's just going to take that 1 and shift left all the way through. So I'll just show you how this is going to look. I'm going to put the variables in: clear, clock, load, shift left, input and output. I'll make this full screen, and I'll just so it's easier to read and see what's happening when changing these to binary. And I'm going to run this for 1,000 nanoseconds. Make this big. Okay. So as long as clear is a 1, nothing's going to happen. And on the rising edge, this is a falling edge. So on the rising edge, clock is 1, load is 1, so it's going to put in whatever input has into the load, and it's going to shift left on the next rising edge. So next rising edge is here. So it used to be 0001, now it is 00010. So it did shift left, and then on the next rising edge, it's going to shift again. So it shifts here again. And then on the next rising edge, it shifts again. And then one more time, shifts again. So that's basically part 1 of homework 7, shift register. Thank you. Hello and welcome to homework 7, part 2. Here we are supposed to make a 4-bit counter that we can have its value reset to 0. It can increment and it can decrement. And so here we have a 4-bit counter. Here's my VHDL code. The ports are clock, reset, an increment, a decrement, and a load. It has a 4-bit input and a 4-bit output. And here I have the process. Whenever the reset is 1, the current value is going to the counter is going to reset, and the load is just here to take in that input, the 4-bit input, and set it to whatever the current counter will be. And if increment is 1, is going to increment by 1. It's just going to add 1 to the counter. And if decrement is 1, is going to subtract 1. And that's what this 4-bit counter VHDL code is. And here's my test bench. Test bench, I have signals, and signals are ported to the respected signals to the component. And here I have the clock. The clock is just alternating from 0 to 1. And here I have another process block. It starts off with reset being 1, and so everything else is just 0. And then the reset turns off, and then it increments 0, 0, 0. And then so it's gonna be 0, 0, 0, and then after 200 nanoseconds it becomes 0, 0, 1, and then 0, 0, 0, 1, 0. So and then after about 400 nanoseconds it starts decrementing, So it just goes back to 0 again. So I'll just show you the simulation. I'm going to add a reset, clock, increment, decrement, load, input, and count. And I'm going to run it for about 700 nanoseconds. And I'll just change these to binary so we can see what's happening. So it starts off with reset being 1, so nothing is happening here. And this is a falling edge, so nothing happens here. And then on the next rising edge, clock is 1, increment is 1, and load is 1, so it's ready to load in 0, 0, 0. So actually at the next rising edge here, it loads in 0, 0, 0. And then at the next rising edge, it's going to add 1. So here it adds 1. And then at the next one, it adds again. And then for the next rising edge, the decrement becomes 1 and increment becomes 0. So it's switched to the subtracting mode, and it subtracts 1. And then at the next rising edge, it subtracts another 1. So that's basically it for this part 2 of homework 7, which was a 4-bit counter that increments by 1 and decrements by 1. Thank you. Hello and welcome to part 3 of homework 7. Here we were given a problem to make a finite state machine that will do 5 functions. It will 1. Clear the register and reset the counter. 2. It will increment the counter by 2. 3. It will decrement the counter by 1. 4. It will load the register with the value at its inputs. And 5th, it will shift the shift register by 2. So here I have a finite state machine code that I have clock, reset, and a input. And I have 2 outputs. One is for the register and one is for the counter. And this VHDL code is just going through each state. And because there are 5 states, I have here a case statement. So whenever it's at the first state, which is 0, 0, 0, it's going to clear the register and reset the counter. So it's going to print out a 0, a 0, 0, 1, and then it's going to go to the next state. And if the input is not a 1, it's going to stay there. And it does that for each state. And here's the test bench I'm testing. I'm just going to run this and show you how this is going to look. Input reset, clock, the inputs, register, and counter. And just run it for about 1,000 nanoseconds. So here we are, make these binaries. So it starts off with reset being 1, and so therefore everything else is reset, cleared. And at the first rising edge, clock is 1, the input is 1, then it goes to the next state, which is 1, 0, 0, 1. And then at the next clock edge, it goes to the next state, which is 2. And then at the next rising edge, it goes to the next state, 3. The next rising edge, 4. And this is the final stage. And because at the next rising edge, input becomes 0, it's going to stay there. And it's going to stay there until that 0 changes back to a 1. And then here, reset is 1, so everything else is cleared. The counter is reset, and the register is cleared. So this part 3 is working fine. I'll see you next on the part 4, where we will implement this finite state machine to control the rest of the shift registers and the counters. Thank you. Hello and welcome to part 4 of homework 7. Here we are supposed to make a top level entity that will connect our finite state machine to the counter and register. Here I've made a top level VHDL code that is going to implement the finite state machine, the shift register, and the 4-bit counter as components. And here is my test bench. I'm going to test the input 0001, and when the finite state machine gets to state 3, it should load this input in to the input of the register, and then in state 4 it should shift it. So let's see if that is true. I'm going to run this. Open the wave and put the variables in, reset, clock, input, the register output, and a counter output. Make these binaries so we can see what's happening. And I'm just going to run it for 1000 nanoseconds. So here we are, the reset is 1, nothing is happening here. And then it hits the state 0. When state 0, it's supposed to clear the register and reset the counter, and it does. So at the next clock edge, it's supposed to, that's going to be state 1, then it's going to increment the counter by 1, and it does. And then at the next clock edge, it's going to subtract by, it's going to add by 2 here, and it's going to subtract by 1 at the next clock edge. So that is what it does. And then at state 3, it's supposed to load in that input value into the register output. And there it is. And then at the last state, state 4, it's supposed to shift the bits to the left twice. And that is what it does. And then after this, it just resets. It's supposed to clear everything out. And that is what it does. So everything is cleared. And that's it for part 4 of homework 7. Thank you very much.